another one is the formation of our report, which is with some distillation. In distillation, a sample is heated to the boiling point of the solvent and volatile analytes are concentrated in the vapor phase, condense, and collect. This approach is mainly used for samples that can easily be volatilized. Problems are that a sample can decompose if heated too high. This means that vacuum distillation can be used for low vapor pressure compounds, while steam distillation is rather gentle since maximum temperature is 1000 degrees Celsius. Distillation refers to the selective boiling and subsequent condensation of a component in a liquid mixture. It is a separation technique that can be used to either increase the concentration of a particular component in the mixture to obtain almost pure components from the mixture. The process of distillation exploits the difference in the boiling points of the components in the liquid mixture by forcing one of them into gaseous state. And also note that distillation is not a chemical reaction, but it can be considered as a physical separation process. Microdialysis is a technique in which semi-permeable membrane is placed between two aqueous liquid phases and low molecular weight molecules transferred from one liquid to the other based on a concentration difference over the membrane. Enrichment techniques such as solid phase extraction are required to concentrate the dialysis. Microdialysis is used, for example, for the examination of extracellular chemicals in living plants and animal tissues and in fermentation drugs. It has been used online with LC dialysis with MWCO membranes can also be used for online deprotonation of samples. Microdialysis is in vivo bioanalytical sampling technique used to monitor the chemistry of the extracellular space of living tissues. Micro refers to the extremely small scale and dialysis refers to the movement of chemicals across a permeable membrane. Next to lyophilization or freeze drying is an aqueous sample is frozen and water removed by sublimation under vacuum. This technique can be used for non-volatile organics. The concentration of inorganic and large sample volume can be handled. A potential problem can be the loss of volatile analytes. Freeze drying is a process in which water is removed from a product after it is frozen and placed under a vacuum, allowing the ice to change directly from solid to vapor without passing through a liquid phase. Water sampling. In the case of water sampling, it is important that collection containers are pre-treated before the sample can be collected. In principle, only polyethylene or PTFE containers should be used and they should be washed and stored in 10% of nitric acid for 2 days and rinsed with double distilled deionized water. Following collection, acidification of the sample, normally with 2 ml of 10% of nitric acid or 5 MHCI, will reduce or eliminate trace element absorption and hydrolysis. Microextraction techniques. Two equilibrium-based microextraction techniques serve as alternatives to classical solid phase extraction. Solid phase microextraction (SPME) and stir bar sorptive extraction (SBSC). Stir bar sorptive extraction is a similar equilibrium technique that requires submersion of a stir bar that is in encapsulated in a glass jacket and coated with a solid phase into the liquid sample. Microextraction is defined as an extraction technique where the volume of the extraction phase is very similar in relation to the volume of the sample, and extraction of analyte is not exhaustive. Membrane technique. Membrane technique. Membrane extraction methodologies encompass both the non-porous techniques of supported liquid membrane extraction (SLM), microporous membrane liquid extraction LLE, polymeric membrane extraction PME, and membrane extraction with absorbent interface HESI, in addition to the porous membrane technique of dialysis. Microwave assisted extraction. Microwave assisted extraction is one of several techniques that has been developed in response to the increased demand for liquids that have a shortened extraction time and reduced solvent consumption. One of the primary benefits of microwave assisted extraction is the ability to directly heat the sample with the application of microwave. This type of heating is fast and temperature agents are kept to a minimum. A drawback to the technique is the requirement for an extraction solvent that is able to absorb microwaves. Microwave-assisted extraction is a process of using microwave energy to heat solvents in contact with a sample in order to partition analytes from the sample matrix into the solvent. Pressurized Pressurized liquid extraction methods frequently utilize accelerated solvent extraction system or any other systems that perform static or dynamic solvent extraction at elevated temperatures and pressures. The advantage of performing extraction under pressurized conditions is that the upper extraction temperature is not limited by the boiling point of the solvent, as is the case with traditional solid systems. Pressurized, pressurized liquid extraction, or is also known as accelerated solvent extraction or pressurized fluid extraction. It is a method of extracting a sample using conventional solvents under high temperature and pressure. Supercritical fluid extraction. Supercritical fluids such as supercritical carbon dioxide, supercritical water are used for extraction as the solubility of materials at supercritical stage increases. Supercritical carbon dioxide continues to be fluid of choice since its critical parameters 31.1 IC 72.8 bar are easily achieved with high pressure instrumentation. Further, it is non-toxic and easy to obtain. Some of the supercritical fluid-based methodologies utilize suitable modifiers to enhance analysis. Supercritical fluid extraction is the process of separating one component, which is the extractant, from another, which is obtained using supercritical fluid as the extracting solvent. In conclusion, the discussion emphasizes the importance of collecting representative samples of food to assess their quality and characteristics. The sampling process involves various steps and techniques to ensure accurate and reliable results for different types of food, whether solid or liquid. Proper sampling is crucial for quality control and safety in the food industry. And naday may mga video for katong examples kani nga comment ni Sir last report.
Hello friends, welcome to my YouTube channel. The topic that I am going to discuss today is solid phase extraction technique, which is also known as SPE. It is one of the most widely used extraction technique in most of the laboratories. Its widely used application is in bioanalytical research laboratory. Bioanalytical research is defined as the analysis of biological samples with the help of analytical technique. Here biological samples are blood, plasma, serum, etc., whereas the analytical technique generally used is LC-MS, that is liquid chromatography coupled with mass spectrometry. In this video, I am going to discuss two things about solid phase extraction technique, namely first, introduction to bonded phase, and second, steps involved in SPE. Now let us first understand introduction to bonded phase followed by steps involved in SPE, that is solid phase extraction technique. If you are new to my channel and you have not yet subscribed, subscribe my channel and press the bell icon so that you can get all the latest updates of my new uploads. Bonded phase is a porous solid on the surface of which analyte from the sample gets adsorbed in solid phase extraction. The bonded phase is used in solid phase extraction to attract and adsorb the analyte of choice, which results in accumulation of the analyte's concentration at the polar surface of the solid. The analyte may interact with the bonded phase due to mild intermolecular forces or electrostatic attraction or by chemical interaction. Now let us understand factors that affect the selection of bonded phase. There are four factors. First, analyte structure knowledge help in the selection for effective isolation. Second, sample miscibility with water or organic solvent. Third, polar or non-polar structure of analyte, and fourth, pH dependability of analyte, that is if it gets ionized with change in pH. Now let us understand the steps involved in SPE, that is solid phase extraction. There are four steps involved in solid phase extraction technique, namely first, conditioning, second, loading, third, washing, and fourth, elution step. Now let us understand each and every step in detail. First step, conditioning. Conditioning of the bonded phase is done to activate appropriate sites for adsorption. The solvent can be pulled through by positive pressure or by vacuum. Second step, loading. Appropriate sample volume is added to the column, allowing it to come down slowly along with the retention of the constituents. Third step, washing. The column is washed to remove all interferences and other matrix constituents. The washing solvent should not interact with the analyte. Fourth and the last step, elution. The last and the final step is elution. It is done with a solvent which has greater affinity for the analyte than the bonded phase. Elution is done slowly to ensure that all analyte molecules interact with the eluent. Thus, a concentrated form of the analyte is obtained which can be used in any other analytical method as a pure sample. If you are watching my video for the first time, please subscribe my channel and press the bell icon so that you can get all the latest notification of my new uploads. Thank you.
The technique of liquid-liquid extraction is a form of solvent extraction which is often referred to simply as a separation, and we do this using a separating funnel as shown on the screen. The technique can be used in a range of contexts, and it's important that you understand why you're carrying out a separation in the experiment that you're doing. In this demonstration, we have a solution of a product of a reaction in an organic solvent, which in this case is diethyl ether. We are going to wash the solution with water to remove impurities which are water soluble. The first step is to remove the magnetic stirring flea from the reaction flask, and we need to wash this with ether to ensure that we don't lose any of our product. We now need to pour the solution of our product into the separating funnel, taking care to avoid any spillages, so it's wise to use a small glass funnel as we pour. Then we can rinse our reaction flask with more ether to ensure that no product is lost. Now we add the water which we're using to wash our reaction mixture with. It's important that you pay attention to your script, which may specify a different solvent and a particular volume that you need to work with. Next, you need to place a stopper in the neck of the separating funnel, and you must ensure that you don't allow this to fall out at any point while you're handling the apparatus. Secure the stopper with one hand and carefully invert the separating funnel. Now you can gently shake the funnel while periodically opening the tap to release pressure. Normally you carry out these steps several times to ensure thorough mixing of the two layers. And then with the tap closed, you can carefully replace the funnel in the ring on the clamp stand. Here you can clearly see the two separate layers in the funnel. In this case, the denser aqueous layer is at the bottom and the ether layer is on top. However, you should never make assumptions about which layer is which, and you may be given instructions that tell you how to test which layer is organic and which is aqueous. Before running any solvent out of the funnel, you must first remove the stopper. Not doing so is a common error which will prevent the solvent from running freely. Now you should place an appropriately sized conical flask under the separating funnel before carefully opening the tap to allow the lower layer to run out. You should watch patiently as the interface between the two layers moves towards the tap so you are able to stop the flow once all of the lower layer has been removed. Remember that in this case the lower layer was the aqueous layer. Now you can remove this flask and place a second clean conical flask under the separating funnel to collect the upper layer. As always, you should check your script to see what you've got to do next. You may be expected to return one of the layers to the separating funnel to carry out further extraction steps. In this case, however, we are simply going to dry the organic layer using magnesium sulfate. Other drying agents that may be used could include calcium chloride and sodium sulfate, so make sure you read the script before proceeding. If the drying agent forms clumps as shown here, that's a sign that the solution is still wet and that more drying agent is required. When you can see a snowstorm effect like this, you know that the solution is dry and that no more drying agent is needed. You can now remove the drying agent by gravity filtration before consulting the script once again to identify your next step.
Today, we're going to demonstrate how to reduce a bulk sample of aggregate into approximate equal portions using the quartering method, which is performed to create a convenient size sample for testing in a manner that represents the bulk specimen. The quartering method is generally used in situations where an adequate mechanical splitter is unavailable. The quartering apparatus should consist of a scoop, shovel, or trowel with a straight edge, a broom or a brush, and a 6 by 8 foot canvas blanket. For this demonstration, we will be dividing a bulk sample in accordance with ASTM C702 and AASHTO T248 standards, using the Gilson HM275 quartering cloth kit. To divide a sample, you first place the sample on a spread-out canvas blanket. Now mix the sample by turning the entire sample over 3 times until the sample is thoroughly mixed. Shovel the sample into a conical pile by depositing each shovelful on top of the previous one. Flatten the pile to a uniform thickness and diameter by pressing down with the shovel until the diameter is approximately 4 to 8 times the thickness of the pile. Now divide the flattened sample into 4 equal quarters with a shovel or a trowel. Next, remove 2 diagonally opposite quarters, making sure to remove all the fine material. Continue mixing and quartering the material in the same fashion until the desired sample quantity is obtained. An alternative quartering method is by inserting a straight stick under the canvas, dividing the sample into 2 equal halves. Then slide the stick under the canvas at a right angle to the first division, lifting the stick until the sample is divided into equal quarters. Save the unused portion of the original sample until all testing is completed. For any questions concerning dividing aggregate samples or for any other Gilson product, please contact the Gilson Technical Support Team.
Hey everyone, Andy Robertson here with CQE Academy, and in today's video I want to share an important topic called acceptance sampling. Alright, let's head over to the computer and get started.
Alright, let's quickly review the agenda for today's lecture. So I'm going to start with a brief intro to acceptance sampling, what is the history, the background, sort of the approach here, and then we're going to go through a few different examples. So the most popular standard for acceptance sampling is ANSI Z1.4, which is the standard for attribute data acceptance sampling. We're going to go through 1, 2, 3 different examples so that I can walk you through some of the nuances of the standard. And then I'm going to talk about double and multiple sampling plans. So the very first example we do is actually going to be sample size code letter L with an AQL of 1.0. We're going to look at that same example, that same scenario, but for double sampling and multiple sampling, and so you can see how the sample size changes and become familiar with some of the benefits and the downsides to double and multiple sampling. All right, let's get into this. So acceptance sampling is a practice where we take a sample from a population and we test that sample, and then we make a decision to either accept or reject that entire population based on the results of the sample. So this originated in the 1930s, and it really became popular in the 1940s, especially during the war, when the U.S. government, for example, was testing munitions to make sure that the quality of that product met their standards. In fact, the original military standards from the 1940s have morphed into what we call the ANSI Z1.4 and ANSI Z1.9 standard that we use today. And really it became the compromise between destructive testing or 100% testing and some sort of sampling process. Now, anytime we're sampling, anytime we're doing inferential statistics, there's always some risk that we might make the wrong decision. So in a future video, I'm going to explain the risks of acceptance sampling. I'll talk you through the OC curve and help you understand what this curve means and how we measure producers' and consumers' risks. But just for now, understand that there is some risk in the acceptance sampling process, that we could reject good material or accept bad material. All right, so let's get into this and talk about the ANSI Z1.4 standard. So I want to use an example to help you understand the standard. There's actually 2 tables here. The first one here on the left is called the sample size code letter table, and the table here on the right helps you translate your sample size code and your AQL into a sampling plan. So let's do this example. So we have a lot size of 8,000 pieces and an AQL of 1.0. So let's talk about what that sampling plan would look like. So the first thing you do is you have to come over here to your sample size code letter and you have to find your 8,000 pieces. So for example, it would fall into this category here. And you come across to the right, and the default level, the default sampling plan or the sample size code letter is associated with general inspection level 2. So we're going to stick with that today, and our sample size code letter is L. And then we come over here to this other table and we find our sample size code letter, and that tells us how many samples we have to pick. So we have to test 200 units from the 8,000 piece lot. Now we can pair that up with our AQL 1.0. So here we are at our AQL 1.0. By the way, AQL today stands for Acceptance Quality Limit. Back in the original military standard, it stood for Acceptable Quality Level. And that word acceptable quality level led to some serious misinterpretations around what AQL means. So the formal definition of AQL is the worst tolerable process average that is still considered acceptable. So this 1.0 AQL is the worst tolerable process average of defects that you would still consider to be acceptable. And the way this table works is you start with your AQL, you come down here to your sample size code letter, and what you find are two numbers, 5 and 6. And these become your accept and your reject criteria. So when we take the 200 samples, if we find 5 or fewer defects, we can accept that entire lot. If we find 6 or more defects, we have to reject that entire lot. Does that make sense? And then when you're picking your AQL, it really has to be risk-based. So you have to think about the quality attribute that you're inspecting for, and you have to pick that worst tolerable process average for that defect, and it has to align with your overall risk management strategy. All right, so let's now change our example here a little bit to help you understand the nuances of the table. So now in this next example, we have a lot size of 200 with an AQL of 1.0. So our AQL isn't changing, our lot size is. We come over here to this sample size code letter table. We have to inspect sample size code letter G, which if we come over here is 32 pieces. We can then pair the sample size code letter G up with the AQL of 1.0. And what we find here is actually a downward arrow. And what this downward arrow means, and this is true for every downward arrow in the standard, is that we actually have to move down to the next sample size plan down here, which is actually sample size code letter H, sample size of 50, and an accept reject criteria of 1 and 2. So of the 200 lots, we have to sample 50 of them. We'll reject the lot if we have 2 or more defects. We'll accept the lot if we have 1 or fewer defects. All right, let's go through another nuance here. All right, so our lot size is 30 and our AQL is 0.4. So again, we start over here at our sample size code letter table. We find our sample size code letter D. We come here to the plan. D translates into a sample size of 8. And we come over here to a 0.4 AQL. And what we find here is a downward arrow. So the way this downward arrow works, again, is we come all the way down to sample size code letter G, meaning that we have to sample 32 pieces. Now remember, our original population size is simply just 30, meaning we have to test every piece in this lot. And we only accept the lot if we find 0 or fewer defects, and we reject the lot if we find 1 defect or more. All right, does that make sense? Let's do one more example here. So our lot size is 200,000 pieces, and we want to pair that up with an AQL of 6.5. So again, everything starts over here on this table. We find our 200,000 piece sample size code letter to be P. We come down here, we see P. It corresponds with a sample size of 800 units. We pair that up with the AQL of 6.5. And essentially what we find is an up arrow, which means we have to travel all the way up. And our accept reject criteria is 21 and 22. And our sample size actually changes to code letter L. So of the 200,000 pieces in our population, we have to sample 200 units. And if we find 21 or fewer defects, we accept the lot, 22 or more, and we reject it. All right, does that make sense? Now let's move on to double sampling, because I want to help you understand the pros and cons of double sampling. So we're going to go back to that original example of a lot size of 8,000 with an AQL of 1.0. This sample size code letter doesn't change. So we're still going to find ourselves with sample size code letter L. But let's see what the double sampling plan looks like. So this double sampling table is obviously different than single. And let's go to our sample size code letter L. And what it says here is there's a first sample and a second sample. Now each of those samples have the same quantity of 125 apiece, and cumulatively, if we take both samples, we're going to end up taking 250 samples. If you think back to single sampling, we were taking a single sample of 200 units. So if we end up taking both samples, we'll actually take more than the single sampling plan. But the beauty of double sampling is that oftentimes the quality of our product is so good or so bad that we can reject or accept the lot just based on the single sample. So again, here's that AQL of 1.0. Let's find that intersection between L and 1.0. And so when we take that first sample of 125 pieces, if we have 2 or fewer defects, we can accept the batch on the first sample. If we have 5 or more defects, it means the quality is really bad and we can reject the whole lot based on that first sample. If we have 3 defects or 4 defects, we have to take another sample. That's the second 125 pieces. And you'll notice here that the accept reject criteria for the second piece is 6 and 7. And this is cumulative. So let's say you have 3 rejects during the first sample, meaning we have to take a second sample. And then you have another 3 defects when you take the second sample. Cumulatively, you had 6 defects, which means you'd end up accepting that batch. The inverse of that is, let's say you had 4 defects the first sample and 4 defects on the second sample. Cumulatively, now you had 8 defects, meaning you'd have to reject that whole batch because you had more than 7 defects. So that's double sampling. And like I said earlier, the benefits of double sampling is that oftentimes you can accept or reject the batch just based on the first sample, which over the long run, if you calculate the average number of samples that you take, is actually less than single sampling. The downside is that sometimes it can be difficult to administer. Maybe you have to go out to your warehouse and take a sample and come back, and go out to your warehouse and take a second sample. And because of some of those inefficiencies, double sampling doesn't always make sense for everyone. And then we can stretch this idea of double sampling all the way to multiple sampling. So a multiple sampling plan is simply just an extension of double sampling where we can take up to 7 different samples. And each of these samples that we take has its own accept reject criteria. Now the example I'm showing you here is the multiple sampling plan for the sample size code letter L with an AQL of 1.0 because I want to show you the differences between single sampling, double sampling, and multiple sampling. So here we're going to take 7 samples of 50 pieces, meaning cumulatively, if we completed the entire sampling plan, we would have a sample size of 350 pieces. Now, if you think back to single sampling, that's 200, double sampling was 250, but again, the logic of multiple sampling is still the same. We can oftentimes make accept or reject decisions early on in the process so that the average sampling that we take over time is actually greatly reduced. So let me explain how this works. So in this first sample, the accept number is actually NA, meaning we can't actually accept the batch on this first sample. What we can do is we can reject the batch on that first sample. So if the quality of that batch is so bad that we have 4 defects within 50 pieces, we can immediately reject the entire batch just on that first sample. Now it's in this second sample of 50 pieces where we could actually accept the batch if cumulatively between the first sample and the second sample, we had 1 or fewer defects. And then of course we can always reject the batch with 5 or more defects. But if we end up having 2 defects or 3 defects or 4 defects, we actually have to take the next sample. And so this could go on and on and on and on depending on the results that you get, all the way down to the final sample where we accept on 9 and reject on 10. So this is that idea of multiple sampling. All right, that was it for today. I hope you enjoyed it. If you did, hit that like button so other people just like you can find this exact same content. And if you want to continue on your journey of becoming a CQE, hit that subscribe button so that as I publish more content, more tools and tricks and training material, that you get access to that stuff immediately and you can learn and you can grow. All right, thank you so much. I'll see you in the next video. Bye.